Test. Hello. What telephone? Did anyone hear me? Hello. Hello. All right. Can everyone hear me? Yes. Do I have to? Oh, cool. Oh, yay! There are people. Thank goodness. Cool. All right. Let the experiment begin. Cool. Okay. Let's wait 1 more minute. Oh, I hear someone else. Okay, so hopefully you guys know how to do all the weird raising hand thing. Because I hope people will, participate. But I guess we'll just get started. All right, this is weird. Welcome back to 365. We're gonna talk about topic models today. Obviously, I have some big news about the syllabus change and logistics and whatever. So I will get to that very quickly. I will sort of go over topic models. Obviously it's been spring break and how do you raise your hand? I have no idea how you raise your hand. Does anyone know how to raise their hand? I have a feeling I can't raise my hand, so I don't know how to check that. All right, someone figure that out. In the meantime, I posted the slides on Canvas, I think, so you can follow along at home. Okay, so few big updates. Yeah, sorry, I've been sick for the past 2 weeks, and I still have a cough. Thankfully, actually, this is online, so you guys wouldn't be worried about coming in to see me. So yeah, I have a bunch of emails I need to get back to people, and obviously I need to set up administrative stuff, office hours, homeworks and whatever. So I thought a lot about this, and I basically have decided that sort of, in sort of the stress that we're all in right now, basically I will be killing off the midterm/final. So we won't have a midterm or final. Hopefully that's good news, not bad news. Yeah, so I think, in general, like finals are great, but obviously it's stress inducing, and I don't want people to be stressed and then end up getting sick as a result of this. So instead, what I will have is basically more mini quizzes, the details of which I am not too sure about, because obviously, a lot of people won't have access to sort of like iPads or printers and stuff. So I don't want it to be something that you can write. So I want it to be all online. So I need to figure out how to set that up. But it will be mini quizzes just basically to keep you guys on your toes. And originally I was thinking about doing a final project instead, but I think what I'll do is have basically sort of like an extra question for the homeworks that sort of allows you to be a little bit more open-ended, and if you're interested, sort of do some more interesting types of problems. So that will be the format. Any questions about that? Oh, okay, yeah. So also the actual in terms of like grade distribution, I need to figure out how to do that. So sorry. Yeah. So any questions regarding that? No. Hopefully you can tell if someone is raising their hand. Everyone's still alive. Okay, cool. Okay, no questions. Cool. Okay, so this will be the, oh yeah, so as a result, I pushed back the assignment deadlines as well. So you're, sorry. So your first assignment, fifth assignment will be due next week instead, because as I said, like, I have a feeling people are struggling with topic models. We sort of didn't really cover it too quickly. So yeah, so this will be the format of the last few weeks. As we said, this is sort of the harder half of the class. We're talking about topic models and move on to language models, word embeddings, bunch of acronyms, neural networks, deep learning, backprop, and we'll see how things go in terms of like selected topics. Okay, cool. Any other questions? Everyone? Anyone? Okay, no questions. Cool. Here we go. So let's move on. Let's go revisit topic models again. Okay. Also, hopefully my internet is good. If not, please let me know. All right, so let's try to remember what the whole point of topic modeling is, right? So the idea is you have a set of documents and, let's say 200 documents. This could be scientific articles, and they're just a bunch of text, right? And so the goal here is to do a classification problem on these documents in an automated manner without actually understanding the meanings of the words, but actually sort of taking into account sort of the relative frequencies and co-occurrence of words in your documents. All right. And so the way we're going to figure out how to sort of calculate, like create these classifications, is we're going to basically take a Bayesian approach where we, and this is, this is sort of the weird thing. So I am definitely reiterating here. There's the weird thing where we're basically going to take this generative model, and I'm going to describe this again. And the key point is that this generative model is clearly wrong, right? The interesting thing is that even though it's clearly wrong, even in that case, you're still able to get interesting results that come out of inferring the parameters of that model. Okay. And it's actually a little bit complicated to see why, I've said this last lecture, why it's the case that even though you have a shitty model, you can still get something interesting back. Okay, so let's go ahead and describe what the model is again, right? So the model here, this is a sort of a different pictorial representation of the model. What we can think of is basically you have these various topics, right? Remember, what is a topic? A topic is a distribution over your vocabulary, right? What is a vocabulary? Actually, there were some questions on Piazza about this, right? So you should always think of it just a vocabulary as this master list of words that you're just going to consider, and everything else is basically a non-word, right? So you have this master list of words. You usually want to do some pre-processing to want to reduce the size of this vocabulary list, because you don't actually care about a lot of these words like the or is, right? And so you have this master list of words, and then the vocabulary is literally just a map from that list of words to a number, right? So it's essentially, you can think of it as like a one-hot encoding for this really, really large classification categorical data set. Okay, so you have your vocabulary, and then once you have your vocabulary list, what is a topic? A topic is literally just a distribution over that topic, right? In particular, intuitively, we can think of a topic as basically as like, the most probable words in that distribution. So here you have a, topic one is like something about finance or banking, right? So, okay. And then what you're going to do is that you're going to, in order to create a document, each document is basically going to be a distribution over topics, right? So in this first example, document one is all from topic one, right? So let's look at document two. Document two is more interesting here. Document two, you have a set of words, and what you first do is you first draw a topic label, right? Here in this first case, I can use my fun thing here. Okay, so, right, so you can use, basically, here is the topic label for a particular word. So the first thing you're going to do is you're going to generate these topic labels, right? And then once you generate the topic labels, you can then going to just draw words from that particular topic, right? And that basically gives you your document. Okay, so so that's basically the probabilistic generative model for the topic models. And as we saw last time, actually probably would want to bring up that slide again. We can go back later to it. Okay, so that's the model. And then the key point is that what we do is we basically work in backwards, right? What we see is we see the documents and we see the words themselves, but what we don't see are the topic labels. Neither do we see the distributions of topics per document, and neither do we see the actual topic distribution. Right, so this is basically, the question marks here are the hidden variables for our model, and we basically need to figure out what were the actual variables that were used in generating these documents. Okay, no one's had any questions, right? Or have I just been ignoring everyone's questions? Okay, cool. Okay, again, so this is just refresh for everyone. Okay, and then sort of what we ended up on was basically looking at this graph. And I think it's helpful to refer to the generative pseudocode that I set up here, just to have a one-to-one thing there so you can see actually what's going on. Because I think the generative code is much more useful here. But I assume you guys all have that on in your notes. But so let's just work through this document. This plate diagram, right? So so far I've been talking very intuitively. In reality, obviously, we're dealing with random variables here, right? So it's a generative model, it's a Bayesian generative model. So you have the random variables, and each of these random variables is going to have some distribution, and it's going to depend on the other random variables. So here you want to be careful about sort of how everything relates to each other, right? And you know, that's sort of what is going on in the first question for the assignment. Okay, so yeah, so I think I already went through this. Just again, to refresh, the key point here is that this is the data that we see, right? These are the unobserved, these are the hidden variables. And these all have distributions. These are going to be multinomials. These are going to be Dirichlet distributions. And the blocks here correspond to the number of actual variables there are, right? So if you think about it, we have k different topics. So there are k betas, right? We have d different documents. So there are theta 1 to theta d per document topic proportions. And then once we're inside a document, there are n words. So this corresponds to the topic assignment, and that corresponds to the observed words. Okay. And what do the arrows represent? The arrows represent basically sort of I mean, intuitively, it's like what you need to use to generate these things, right? So in order for me to generate my W's, which are the words, what I need to know my ZDNs and my beta Ks. You know, so, you know, basically what we have is like, it's a multinomial distribution with beta ZDN, something like that, right? So this is why, you know, we have these arrows, because in order to generate the WDNs, we need the ZDNs and the beta Ks. Okay. Oh. Okay, so there's a question. I don't quite understand how words are assigned to topics. Don't quite understand how words are assigned to topics. Let's do, okay. Does anyone want to volunteer to answer this question while I drink some water? I mean, or I could just drink and answer.
I could give it a go if you'd like.
Sure.
So each beta K is, as I understand it, a probability measure on all the words. So beta K assigns each word a certain probability. And in a topic, some words are much more likely, and those are kind of like the top words in that topic.
Yep. Right. So yeah, exactly. Yeah, so it's a little confusing, I guess, because a lot of times I'll say intuitively when I think of a topic, I think of just like some keywords, but really it is just a probability distribution of your vocabulary. Cool, nice. Okay, so let's move on. So blah, blah, blah. So here I just said already, these basically arrows represent dependence. So, you know, the key point of all of this, including the generative pseudocode, is that we basically want to set up this joint likelihood, right? Right. So let's think about what we're doing. In one way to think about, I think the intuitive way for me to think about this is topic models is this generative model. You have these parameters that eventually, you know, you generate all these things that eventually generate the words, right? But at the same time, the other way you can think about this is that it's just basically a bunch of variables that are, you know, jointly distributed in some particular manner. And so you can look at the joint distribution of these random variables, and this basically gives you that, right? So yeah, so you have your betas, you have your thetas, you have your z's, you have your w's, and the conditioning basically is what you would expect given what you need to generate those random variables. Okay. So now this is sort of where the Bayesianness comes in, right? Because what you have is you have a joint distribution, right? And you can think of this as your joint distribution, and you also have your data, which is the W's, right? So and if I wanted to figure out what the parameters were, I would then basically do, well, how do I think about this as a Bayesian? I look at the posterior of my parameters given my data, right? So basically all of this is set up so that you can think like a Bayesian and basically calculate the posterior of these hidden variables, right? So namely these betas, these z's, these thetas, these are the random variables that are hidden. Okay. Right. So in particular, so I just said that, right? These are the three hidden random variables that we're going to use, right? And so what we're basically going to look at is this probability of z dn's, theta d's, theta k's, given my w dn's, right? So this is, it should be clear. I mean, I'm not sure if it's clear, but I think if you were to look at this posterior, you might be like, okay, this is going to be ridiculous. This is basically impossible, right? And it turns out, yeah, basically, if you were to deal with this thing directly, it is basically impossible to deal with, to calculate this posterior. And so there are actually a whole bunch of tricks you need to use to basically get at the posterior for what we want. Okay. But this is sort of just at, at a high level, this is the flavor of Bayesian analysis, so latent variable type modeling, right? What you do is you have a data set, you have some type of data, and you just basically set up a generative model that you think sort of gets at the principles behind how your data is generated. And in particular, you set up your hidden variables, these latent things in such a way that the actual values of these are meaningful to you as a human, right? And so once you've set up this generative model, you're always able to then calculate a posterior, right? Literally, it's just, right, from my generative model, I can calculate this posterior. Once I've defined this posterior, then I can always calculate, my posterior given my data, right? And so the whole point of all of this is that once you're done with that, then it's just a computational matter, and you have to do some tricks, obviously, but you're basically done, right? The posterior gives you all the information you want about these parameters, and that's all we're going to learn. Okay. So hopefully you guys have sort of immersed yourself in the Bayes notes that I sent out a few weeks back. So this should be familiar to you guys. Okay. Any other questions? Cool. I'm not going too fast, right? Maybe I'm going too slow. Okay. So as we said already, the Dirichlet is a distribution that we're going to use because basically this is what we want when we sort of extend things from a die to from a coin to a die, right? Whenever we want to set up a distribution over many categories, which is basically a probability distribution over a k-sided die, then you want to use the Dirichlet distribution because it's the conjugate to the multinomial. Okay, and throughout all of this, we're going to set it up such that the alphas for the Dirichlet, the parameters are basically going to be identical, so we don't have to worry about anything. And as we'll see, basically sort of it controls the shape of the final distribution. Okay, so as we saw last time, right, what we have is we're going to set this up in such a way that, so when alpha equals to 1, it's like sort of not particularly informative. As we increase alpha, we're basically going to get a converge to a fair-sided coin die, fair die, which is sort of not what we want, right? So actually what we want is we want something, I guess, that looks a little bit like this, right? Like if you think about what's going on here, so for instance, if you think about this in terms of the vocabulary, so your topic, right? A topic is a distribution over your vocabulary, right? So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here I have a 10-sided die, but it should be a V-sided die, right? And I sort of want it to be sparse in a little, like sort of sparse, because I basically am trying to suggest that topics are mainly a few keywords, right? So that's why this Dirichlet is nice, because it's able to sort of capture that type of probability distribution, right? So this is also why we end up just having the alphas to be the same, because we don't really care about the individual words themselves. What we just care about is sort of the general sparsity of our final distribution. Okay. Cool. No questions. Very nice. Okay. So I have some notes on this. This is actually. So alpha was a vector group. Yeah. So sorry. Yeah. So what I'm saying is that alpha is right. Alpha is actually a vector, but because I'm setting all to be the same, so I'm just, in this particular example, I'm just saying, well, this is the alpha. All of them are 0.001, right? So yeah. So I'm just being lazy here and saying that throughout whenever I talk about alpha here, I will always only just have it to be identically the same number. But it actually, when you set it up in a Dirichlet, you need a vector, but it's just going to be all the same number. So here, they're all the same number, and they're equal to 0.001. Okay, so it's the same thing as in the assignment where I wasn't that clear about whether or not you could set up alpha to be different or the same. So alpha is always, the individual components of the vector of alpha are always going to be identical throughout this class. Okay. And yeah, so, and it's also like, you should also think about like why that is fine. Because essentially, well, okay, so for your own self, you can think about why it suffices to have that restriction. Okay. Sorry. I just had a funny question. Okay, so okay, so the question is, can I have a practical example? I guess I'm not sure, like, I guess I'm not sure right now what, so okay, so throughout all of this, you should be keeping in your mind the example we have throughout, which is the abstracts where you have, 200, the first 200 words for your abstracts for scientific articles, and this is the general model for that, right? So yeah, I mean, okay. Right now, unfortunately,
No, I was just wondering if it was easier to just ask the question directly. And I don't mean to interrupt the flow. I was just thinking that, like, because the concepts are a bit abstract themselves. So keeping an abstract example in your mind with an abstract concept that you're trying to always link abstractly, I think it's a little bit, I mean, it's possible, the homework helps, but it might be useful to have maybe a 2-paragraph story that we are walking through that just kind of like helps you just connect. I don't know how easy or difficult the homework would help us do that, but like, it's just where I think I'm spinning my wheels, not if no one else is anyway.
Yeah. So yeah. So unfortunately, I do think. I mean, this is why I think this topic is hard, because, and actually, what I will eventually do is give a summary of this, because there are actually a lot of moving parts to this. I mean, as we said, like, we've so far only talked about the generative model, which ultimately all it does is set up the joint distribution, right? So I don't know how helpful it is to have an actual application like on the side, but in my mind, I am like, every time I have these Z's, betas, W's, you really should just be thinking about this in terms of like some document, some topics, fix some vocabulary in your head. Yeah. Okay. So. Okay. Yeah. So I guess if you have anything in particular you don't understand, please just ask me, because I'm not really sure how else to make this more concrete. Okay. Okay. Yeah. Cool. So I actually might skip this because I think it's well, okay. Let me just go over this a little bit. I think it's actually a little bit subtle. So I don't want to confuse you guys. I think right now the most important thing is to get through the actual sort of the meat of the algorithm. But you might ask the question as to essentially why does, so okay, LDA, which is like latent direct allocation, is the sort of the general name to describe this procedure where you have some latent distribution. So you have some latent variable model and you use the Dirichlet distribution as the latent variables, right? So this is why it's called latent Dirichlet allocation. So topic models, the thing we're teaching you now would be called a latent Dirichlet allocation model. Okay. This is a little bit subtle, so I won't spend too much time on it, but I think this is actually a really important question, and it's a little like hand wavy, obviously, but like ultimately the question is like, why does this generative model even give us anything interesting, right? Like, why is it the case that if I run this generative model, if I have this joint likelihood and I calculate the posterior, why is it the case that this is then going to actually set up my hidden variables in such a way that I'm going to have actual meaningful topics, right? So for those of you who have actually run the homework, hopefully you'll see that when you actually run these topic models, if you run the algorithm, it's actually going to, give interpretable topics that come out from the model itself, right? But if you think about what the posterior is doing, the posterior sort of doesn't really know any of that. Like, it doesn't, it's sort of doing it in a very abstract mathematical way. But all I've done is set up a generative model, right? Which, again, to reiterate, all that is doing is setting up a joint distribution, right? A joint likelihood. And then once I have this joint likelihood, all I do is calculate the posterior given the data that I see, right? And that's just some distribution. And it's still a little surprising it's a little magical why, even when I do this calculation, it should be the case that the final things that come out of it are actually meaningful in the same sense that we think of these as meaningful in terms of classification. And so this slide gives you a little bit of intuition as to why this might be the case, right? So yeah, so the idea is that, ultimately what you're trying to do is you're trying to maximize the posterior, right? You have this posterior distribution and you want to fit your data in such a way that you sort of maximize the posterior. And so what you're going to get is that ideally you want to set word probabilities. So the word probabilities are going to be maximized if you have, okay, so let's think about how this is going to work. Okay, so here's a question. So for example, is the p theta given w the result we get from the posterior a specific PDF for a directly distributed variable that we think corresponds to our data? So yeah, so actually this is why it's a little bit complicated than that, right? So okay, so what's the question here is, what you could potentially look at? You could potentially look at, let's say, like the theta d's given w, right? Okay, so first of all, actually, really what we're looking at is all of them, right? Which is what? Z dn and beta k's given w. Right, but okay, suppose we could actually extract this out, right? So this is why actually it's a little bit more complicated than just doing these conjugate type things. And the reason is because all these parameters depend on a lot of things, right? So it turns out there's some simplifications, but you can't just go directly here, because in order to relate the thetas and the w's, you need to have the z's and the betas, right? Because that's, how do the distribution of the words relate to the theta d's? They relate through the z's and the betas, right? Well, in this case, they relate through the z's, right? So I mean, I will go through this in a little bit. It's not just a very simple calculation where you're just calculating the posterior and it turns out the posterior is just a Dirichlet distribution, right? Okay. In which case, I think I will actually just skip through this slide because I think it's going to confuse people. Let's go through the actual derivation of what you need to do to get LDA to work. Okay. Right. So I've already went through this. This is the key thing we're going to have to calculate, right? This is the posterior. We want to calculate this. And as we know from Bayes' rule, what we can eventually get is we actually want to calculate this expression, right? So here we have this joint distribution, which we know the form of, right? We know the form of that because that was basically the whole generative model sequence that we were working with, right? The problem is there is no way we can calculate this, right? And this is, when I talk about Bayesian statistics, I talk about the computational problem. This is the computational problem, right? It seems like we're, this is literally all we need to do. If there was some magical way we could calculate this distribution, we would be done. Like that would be the end of this topic. All I need to know is understand the posterior, right? If I have this distribution as a function of the data, then I know, what are my most likely betas, thetas, and z's. The key point is that in order to calculate this distribution, right? Again, it's the posterior distribution. I would first rewrite it in this way. I can write out this numerator, but I cannot calculate the denominator because it's just too ugly. Right? It's an integral over these betas and these thetas, and it's just ugly. So the question is, how can I approximate calculating this denominator so that I can get something that is akin to the posterior distribution? Okay, and that is essentially the crux of Bayesian statistics. So actually, a lot of Bayesian analysis comes down to computational tricks to calculate this denominator in your Bayes rule. Any questions? Cool. Okay. Okay, so I guess let's think of this in terms of applied way, right? So what I'm saying here is that if you think about this in terms of the homework, right? The W's are the text of our documents, right? And these betas, these thetas, these Z's are the particular parameters that we're interested in, right? And what we want to know is we want to know a distribution over these parameters, right? What does that mean by distribution? That basically means I want to know the probability of these variables being a certain value for all possible values, right? That's the distribution. That's what I mean by distribution. Once I have this posterior distribution, I can then find, the posterior mean of this distribution to find the most likely values of the betas and the thetas and the z's. Okay, so I need some more water. Ooh la la. Okay, so now here we're going to go and sort of talk about how to basically approximate this posterior. It turns out that, okay, there are many ways to do this. For the latent Dirichlet allocation, it turns out we're going to look at one particular way, which is basically Gibbs sampling. We're not going to look at this mean field variational method. That's not important. We're basically going to look at Gibbs sampling as a way to approximate this posterior. Where is my, okay. So, this section here is like basically the crux of like stochastic processes. So if anyone's taking stochastic processes, hopefully this will be, secondary nature at this point. But essentially what we're going to, so intuitively what we're going to try and do is we're going to try and basically set up a sort of this process, right? So it's like, it's a process in such a way that this process sort of approximates sampling from this distribution. Okay, so actually, so here, let me give you, it might be helpful to give you a example. Right, so ultimately, so what we have is a posterior, right? A posterior is just some distribution. Think of this as like a 2D one. That was not right. So this posterior is basically a 2D. Sorry, suppose I have a 2D graph. Okay. Let's say X. No, Y is X here. Let's say X and Y, and this would be probability of X, right? So my point is that okay. When I say posterior, I basically mean distribution. I want to find out what the distribution of something is, right? And the point is that I don't actually have a closed form solution for this distribution. So I don't actually know this distribution, right? So an example of something that would be closed form is, suppose I had just a multivariate normal, right? That would be a closed form distribution. And then I can just describe it with just the probability density or the PDF, right? Then if I were to, then I would know everything about this distribution. The point here is that the posterior that we have, right? So we have this posterior, which is really, really ugly. We don't actually have access to the closed form solution for this distribution. But what we can do is do something a little bit worse, but hopefully something that can give me something a little bit close, right? What I'm going to do is, suppose I don't have access to this distribution, right? Okay, also, if anyone's not understanding, please let me know, because this is really important. And it's, again, this is a very different way of thinking about these types of problems. So if you don't understand it, you will suffer in future. So, okay, so what we're trying to do is we're trying to figure out a way to understand this distribution, but we don't have access to the closed form solution for this distribution, right? But suppose I told you that you had an ability to sample from this distribution, right? Okay, now I'm going to open this up to the floor. If I were able to sample from my distribution, what could I then do to figure out the actual distribution? That was, whoa, someone raised their hand. Cool. Go ahead.
Can I speak? Are Kunle?
Yeah.
Yeah, so I think here what you do is try and get as many samples on the distribution, and then try and like get a histogram of this distribution. And if you really needed to, you could then like, if you could like plot a curve through the midpoints, and you could fit an expression to the midpoints to get a closed form expression. But at the very best, you could at least just histogram the samples you get.
Exactly, right. Yes, so that's exactly the point. Just because I don't have a closed form solution for the distribution, as long as I have enough samples, and actually, so this is a key point. As ideally, I want my samples to be sort of independent, in the sense that I want them to cover the whole space, right? Because if I only get samples that are like in let's say in this region, suppose I only had samples in this region, then I'm not actually going to understand the full distribution, right? Because I'm only going to see points here, and I can calculate a histogram, right? So you're exactly right. What I want is, I want basically to set up a histogram, and I need to ensure, well, I don't need to ensure, but I want it to be the case that my samples sort of span the space of the possible points, right? And the key point is that actually each of these samples are independent. Man, this diagram is epileptic. Sorry. Let's get rid of these. Okay, so this is very this is very important, right? So this is the whole idea of this computational trick, right? Just because I don't have access to the closed form of my posterior, if I can approximate sampling from this distribution, then I'm good to go, right? Because then all I need to do is basically look at the empirical distribution for my samples, and that is my approximation to the true distribution. Okay, and so as someone was saying, the next step actually would be, once you actually have this sampling, right, then you can calculate averages and variances and whatever. Okay. Oh, someone raised their hand. Go ahead, Jake.
Yeah. So is the at the end of the day, the output that we're getting from things like the text to vec function, that's some sort of like modal value from a joint distribution that we're empirically estimating.
Yes, exactly. So yeah, so far I've only talked about the posterior distribution. And actually, as I said, all the information is captured in that, so that's all you need. But obviously, what people report when they run these algorithms is usually the posterior mean. It could be the posterior mode, but usually it's the posterior mean. So that's literally just the mean of my distribution. Yes. Yeah, so that is an important point to make. Okay. Any questions? Right. So this is sort of the intuition behind Gibbs sampling, right? What we're trying to say is I cannot calculate this posterior because it's really ugly. Right. I can't calculate the denominator. Right. So what I'm going to do is I'm going to find a way to just sample from this posterior. Right. If I can find a way to sample from this posterior, and if they're sufficiently independent, then I'm able to approximate the distribution. And so this is a way to do that. And so actually the way I'm going to do this is I'm going to basically look at conditional distributions and sample from them. Okay. So we're gonna give you an example right now. But again, this is I hope the intuition makes sense here, because that's really what's going on and what's driving this computational step here. Later on, the math is going to get a little bit complicated and ugly and painful, but the intuition, I think, is actually not too bad. Okay, so so we're going to stick with this really simple example here and think about how we're going to set up sampling from this distribution. And actually, what I'm going to restrict you is that I'm going to say, not only do you not have access to the closed form solution, you can't actually sample both at the same time, but I can sample them conditionally, right? So what that means is I can basically only sample one variable at a time, provided I condition on the other variable, right? So let's think about what I'm, okay, so can I set up like 2 tabs here? Je ne sais pas. Whatever. Okay, let me just make mini diagrams here. Okay, so Jesus Christ. X and Y, and then sort of P of XY. Right, so I have my distribution that looks basically, ooh, jeez. Okay, so it's like a normal distribution sort of. So what I'm saying is that, hey, suppose it's actually just a normal, it's a bivariate normal with this distribution, right? If I were to sample from this distribution just from this joint distribution, then what I would get is I would get stuff that looks like this, right? Most of my distribution is going to be points like here, right? Because that's where the density is. It's going to be a few outliers, but most of it's going to be here. And so once I calculate my histogram, it's going to look like it's going to converge to the true distribution, right? That's if I had access to the joint distribution. But now what I'm saying is that suppose instead I don't actually have access to the joint distribution, right? What I have access to are these this is like surgery. Okay. What I have access to are these conditional distributions, which is what These are going to basically, it's basically as if you were to take a projection, like a plane, and then so for instance, you could have access to this distribution, right? So this would be saying, what's the probability of y given x equals to 3, say, right? So, so what this would look like, this would actually look like something that looks like this, right? So what I can sample from are these types of distributions. Yeah, so, okay, so when I say we don't have access to the joint PDF, what I mean is that, yeah, we don't have a closed form to the joint PDF, but not only that, we can't sample from it as well. So yeah, so there are two things. We're generally speaking, for Bayesian analysis, you don't have access to the posterior distribution because the denominator is too complicated. So you just don't have access to that posterior distribution, right? So what I was saying is that suppose I could sample from this distribution, then it doesn't matter if I have access, if I have a closed form access to it. But the point is that usually I'm not even able to sample from this joint distribution. What I can hope for is I can sample from these like single variables, right? So what I'm saying here is that, let's look at the example of x and y, and the joint distribution is some bivariate normal. Usually I don't have access to the closed form solution of the joint distribution, so p of x and y. If I could sample from it, then I'd be good, because then I just sample this a million times and I look at the histogram. But oftentimes I don't even have access to sampling from the joint distribution. I can only sample from these conditional distributions, right? So that's basically taking a slice of a plane that's intersecting with, that's parallel to the x or the y plane, right? So what I can do is I can sample from this distribution. Okay, so now what I'm going to say is, here's Gibbs sampling. What is Gibbs sampling is, let's say I set x and y to be some initial starting value. For now, let's just say 0, 0, whatever, not important. Okay, then what I'm going to do is I'm going to basically, because I have access to these two distributions, right? What I can do is I can basically start with initial point of x and y, and then I'm going to sample x given y using the current value of y, and then I'm going to sample y given the existing value of x. Okay, so I will be a little bit clearer about this step. Okay, so let's call this x0 and y0, right? So let's just say it's 0, 0, whatever. Okay, so here is my way of sampling from the joint distribution of x and y. Okay, so first thing I'm going to do is I'm going to set up probability of x given y equals to y naught, right? Because I know the joint, because I know the conditional distributions, I have access to this, right? Because I have access to this, I can sample from it, right? And then let's say, okay, this gives me x1 equals to 2, right? So this is a sampling step, right? I've defined the distribution, I can sample from it, I sample from this, and this is like our norm, right? Okay, now, because I have access to the other one, I can do the same thing, x equals to x1. This gives me now y1 equals to, let's say, -1. Okay, I'm not gonna write this like that. Okay, so now all of a sudden I have an x1 y1 pair. x1 y1 equals to 2 minus 1. I just keep going. Y equals to y1 gives me, let's say, x2 equals to -3. and so on and so forth, right? Eventually I'll get an X2, Y2 pair, right? So through this mysterious procedure, I now have basically collected joint pairs of X's and Y's, right? You remember, what does it mean to sample from a distribution? That basically means I a whole bunch of numbers from, like, you know, like, let's say if it's X and Y, what does it mean to sample from the distribution? It just means a whole bunch of pairs of X and Y's. Yes. Someone have a question? Yeah. You're muted. Hello? Am I? Okay. I guess you accidentally pressed the lower. Okay, I'm gonna lower your hand. Okay, yeah, did someone else? Okay, yeah, go ahead.
If there are multiple modes to the distribution, how could the process guarantee that we don't ignore some of them?
Right, so yes, good question. So far I've just described, I've described the process. I haven't actually said anything about why this thing works, because I was gonna ask, does this thing actually work, right? But I guess, yeah, so the point here is that this is actually, first of all, this is like cheating, right? Because this is not exactly sampling from the joint distribution, right? Because if I were to sample from the joint distribution, what that would basically mean is that I would need to have my X's and Y's to be independent, right? I need the X's and Y's to be independent draws from the distribution in order for me to know that these are actual samples from the distribution, right? But clearly X1 and Y1 are not independent because they are dependent on, you know, because through this procedure, it depended on the previous step. But there are basically, what you can show is that under some conditions, Gibbs sampling basically is a good enough approximation to the joint distribution of your posterior. So to your question about modes, this is actually one of the problems with these types of computational methods. It's the fact that if you have areas of your data where, if it's like very isolated from the rest of your data set, and the chances of actually visiting that from, you know, the main portion of your data is low, then you actually are going to miss these small modes. So yeah, so that so that's actually, you know, there are computational ways to, you know, try to help this. You might actually add a little bit of noise when you're doing this. But yeah, so the key point here is that this is just, oh, so many questions. Okay, so let me just finish my thought here. The key point about this is that Gibbs sampling is one way to approximate the joint distribution. It's important. It's actually good for you guys to think about why this is not actually like good, like why this does not actually give you the right, like the perfect solution. Okay, so someone says, under what conditions do we have access to can sample from conditional distributions? The answer to that is that usually conditional distributions are nice because they're easy, right? What we have is that we're, to sort of skip ahead, what we're going to do is we're going to have our P's and we're going to have our like theta t's, and then everything else is like that, right? So at the very least, it's only a function of one parameter, so to speak, right? I mean, obviously all the parameters are in here, but usually the reason why we like Gibbs sampling is that joint distributions of different random variables is a little bit ugly, but conditional distributions are nicer. So that's why actually Gibbs sampling is used a lot in practice, because conditional distributions are easier to access than joint distributions. Okay, so that's that question. Is x1 the most probable x given y0? No. And then we keep on the right? No. So yeah, sorry. So for those who Zoom glitched, I hope everyone's still here. It's so awkward if I was just talking to myself. So what this is I'm saying that, so okay, this is my initialization, and the key point is that I have access to the conditional distributions, right? What does that mean? That means that all I have to do is set up this conditional distribution and then just take a sample from this distribution, right? This is basically some function. I sample from it, I get some number, right? So I'm not gonna, I definitely don't want to pick the most likely, because then that's not going to get me random sampling, right? I want to be sampling from the joint distribution, so I don't want to be picking the most likely, because otherwise you would just, you know, reach the most likely solution very quickly. Okay. Any other questions? So, okay, the question is, does sampling from a distribution mean imputing random arguments into its PDF? So, you know, like usually, okay, so I don't know if this answers the question, but like when I mean like sampling from distribution, I just mean like R norm, right? What does that mean? That just means that you're, you know, it's like rolling a die, right? It's like what you do is it's basically it's like a pseudo random number generator, except the number you're going to generate follows the density through which you've defined. Right, so literally when I do R norm, I'm sampling from a normal distribution. Here, as long as I give you the form of this conditional distribution, I can just sample. And the way you do that is, you know, you should, in 241, you learn how to like sample from distributions by taking sort of like the inverse of the CDF. Okay. Okay, so this is a lot to take in. Unfortunately, I don't have like, it'd be nice if like this thing had like the Twitch thing where you could like get like responses or something where you could see if people were like confused face or happy face. Hopefully you guys are understanding what's going on. Let me sort of take a step back again, because we're sort of getting into the weeds here. Actually, how much time do I have? Okay, well, I mean, I can, you know, we can go a little bit over. Okay, so okay, so remember what we're doing is we're calculating. We want to calculate this posterior. All right. This is the data that we see. These are the hidden variables. I want to calculate the posterior. The posterior will give me all the information that I want. I don't have access to the posterior directly. So what I'm going to do is I'm going to sample from the posterior in a cute way, where instead of sampling directly from the joint distribution, I'm going to sample them in a conditional distribution manner, right? So sort of one variable at a time. Actually, you know, it's going to be a little bit more complicated than that, but like at least that's the intuition about what we're going to do. Okay. And the goal is that through this procedure, right? So suppose, actually, this is a little important. So suppose I had 3 variables, right? X, Y, Z. What I'm going to do is I'm actually going to go like P of X given Y, Z, P of Y given X, Z, P of Z given X, Y, right? And this is going to keep going. Okay. And in fact, what we're going to see is going to happen is that not only these X, Y's, and Z's are actually going to be individual ZDN. Right, so it's actually going to be like Z11. So it's going to be one variable at a time. So, you know, this is a little bit, this is not exactly what's going to happen, but what you're going to see is actually it's going to be like Z11 given Z minus 11, which means every other Z variable except 11. Right. So, and all the other variables. Right. So, in particular, what I'm saying here is that the way this is actually going to work is that I'm going to do Z11 over, you know, Z12, Z13, Z14, blah, 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 Z21, Z22, blah, 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 right? That's what I mean when I'm actually going to do it one variable at a time. Then once I've sampled from this, I can then sample the next one, Z12, given Z11. This will be the previous, this guy here. This will be all the rest as well. Okay, so that's actually what's going to happen when I'm doing this skip sampling applied to our procedure. Okay. Cool. Here we go. All right, this is the weird and ugly part. Oh, someone raised their hand. Yes.
So so here we did the sampling sequentially. Is it possible for you to generate like a random sampling of all the X's and then like just get the Y's equivalently by running through the conditional of X's?
Sorry, say that again?
I was just wondering, we're doing a sequential sampling when we were trying to do sampling from the partials, right? So Px1 given y1 and then getting x1, y1. Can you kind of do that in a block form? Where you're then sampling like blocks of maybe x1 and 3, you get a set and then evaluate for each x the y's, and that gives you your samples, and then do that for the next set of x. Or use different results.
Okay, so I think your point is that like right, yeah, like is it necessary to sort of like do this sequentially one at a time? Can I sort of do it in a block and then like update the parameters all in one go somewhat? So I think that first of all, I don't think it matters too much. I think in general, this is just a little bit nicer because you don't have to worry about keeping track of like which variables you're gonna keep. So you basically just update one variable at a time and you sort of just work through it. I think it's also nicer here because then you sort of have a cleaner dependency between like what's going on. Is that true? Wait, so yeah, actually, I don't know. So actually, I think it might actually be, yeah, I haven't heard about this before. It might actually, there might be some methods that do implement this. At the end of the day, I don't think it matters too much because you just like tuning the variable a little bit. I think what's nice, I think the reason why you might want to do it in a sequential manner is because you sort of don't want to like, you don't want to accrue your dependencies together. You sort of want to, you know, sample multiple ones and change as much as you can over time. Like as change as much as you can, because you like by changing the parameters, you're sort of moving your what you're conditioning on, and so it's you sort of searching the space a little bit more. Okay. Anyway, that was a little bit kind of weeby. I don't think it matters too much, but at least skip sampling in its original form is in this form and it works well enough. But yeah, good question. Okay. Huh. Okay, so okay, let me see if there's anything. I actually do. Okay, I actually think this is a little bit complicated. So I think we should probably talk about this on Wednesday. If you look at this, this is like really ugly. Okay. Fair enough. Any questions that people have? No questions? Okay. Let's see. So yeah, so for those of you, I guess you guys didn't miss the first part. I sent out an announcement about like details for the assignments and homeworks and everything. Yeah, so it's going to be due next week on Monday. It's on the second page of the slides. Yeah. Anything else? Yeah, how office hours work. So I think we'll for now set this up in just like we'll have just like Zoom office hours and see how that goes. I sort of want it to be possible for people to just have like one-on-one sessions with me or UTAs or whatever, but I need to figure that out. But for now I think it's just going to be Zoom. Yeah, good point. Yeah, so actually, I guess, yeah, so actually it'll be good if so I'll send out an announcement, but it'll be helpful if people can tell me which time zones they're in if they're not in US, because then I can figure out sort of what's the demand for that. And if it's just a few people, then you guys can just come talk to me or something. All right, well, I hope that works out pretty well. Again, I can't tell if people are crying from the deluge of information that just happened, or if everyone's like, this is so easy. Stop wasting our time. Okay. I'm just, well, I'll stay on for a little bit longer in case people have questions after class. Maybe we can go into like break rooms or something. Hope everyone's doing well. And yeah, cool. All right, class dismissed. Anything else? No, thanks. Thanks. Oh yeah, sure. I guess we can just talk.
So, Professor, I was just thinking about this, right? Like in the beginning of the class, you had raised the idea that one of the objectives of this class is like anybody can go and learn these algorithms, like learn the more packages that are online and not know what is in there. But the goal of the class would be to kind of, you would know how to use the packages and then know kind of what's happening on the background or what's happening on the back end.
Yes.
I think
Sure.
the homeworks are helpful in that regard. Like I think what has been my struggle here is that even the packages themselves, as they are trying to use them on the fly, I think they don't even make sense, right? Like I understand the problem, no, but I'm serious. I think I've gone through like using the different websites you sent. Like I understand the problem. And so even learning how the packages solve the problem, all I have is a bunch of example code that I'm trying to match to my problem. And then in class, what I now have is the abstraction of the concepts and the mathematics behind them. So when I was saying an example that kind of walks you through, some of you are never going to go out and develop new code. But even if you were trying to use any code out there, like you're trying to use the TM and you're trying to understand LDA, let me show you like each step of this LDA, even if you don't show us the code, like the pseudocode. Like if we start with the problem, let's say there was one problem I saw online today about you have a mixture of two different novels, and we're trying to separate those novels into like their individual, because some fictitious scenario about one guy the thief tore up all your novels and mixed them up and you had to like figure them out, which I think starts to motivate the problem. So you could take like a few paragraphs from the Wall Street Journal and a few paragraphs from Jane Austen and then mix them together into this two document vocabulary. And then we can walk through just systematically how you go from that to just the end of the topics and the models. And working with pseudocode would make I think then we understand, all right, if I didn't even know any theory and I had to actually do this in practice, I can figure it out. Now, if I wanted to figure it out, like I can then link that example to the underlying, I think it just brings it to life. Because now those two different levels of abstraction, how do I work with the models and the packages, and how do I understand the mathematics, are just two different interactions that it's just hard to kind of follow, at least in the past for LM, and like when we're doing the linear models and all the other topics we did earlier, I could go to a good reference like ISLR or ESL and kind of walk through it. And they actually pepper the exam. They have like a case example that they kind of, at least ISLR has that it walks through. So then I can start to link it. But this one, I think that's some of the difficulty and the frustration. So I mean, maybe it's easy for everybody. I might just be like the dumb one here, which is okay, but I'm hoping that maybe I'm not just the only one and I'm voicing out.
Yeah. So I completely agree, except I guess I just thought that my examples at the beginning were sufficient. So so I think topic models is actually really complicated because there are two parts to it that are basically like independent, right? So the example you gave, the thing you started saying about like, cutting up Wall Street Journal, whatever, that all that tells you is a generative model. Like that is all it tells you. It doesn't tell you anything about how to calculate those probabilities. And that's exactly what the first part of my lectures is, which is that like, let's just describe the generative model and let's give you the intuition for it. And, so this is this slide where we're basically saying, okay, this is how I think about the documents being generated. And this is going to give me an intuition about what this does. And really the only point of it is ultimately just to give me the joint distribution, right? Like I could have just given you the joint distribution and be like, okay, this is joint distribution. From here, we're going to calculate the posterior, right? But I think the reason why topic models is hard is because just because I give you that, just because I give this generative model, that doesn't tell me anything about how to solve this problem. So this is where the second part comes in. And it's hard to bring these two things together because this second step is just it's just a computational calculation. It's like, I mean, all I'm giving you, like, I've told you what I want to do, right? I've told you that I have this problem as an inference problem. I have these question marks and I want to figure them out. Basically, that's literally what we're doing. We just want to figure out these question marks. How do I actually go about figuring out these question marks? It's a mathematical question. There's like, I can't think of an intuition as to why I would, give you for that. So like, yeah.
I hear that point actually. And maybe what I'm struggling with is like, when I'm using a model like QuantAda or like a package, like I'm not even sure where in those packages are these problems being solved at, right? So maybe it's the fact that I get the fact that all of the probability calculations, I'm sure that maybe they're happening because when you run the models in the homework, you're going to get these outputs that have the vocabulary, the probabilities and everything, right? So they're doing all of that. It sounds like they're doing all of these analyses that we're talking about in the background. Correct? Yeah,
right, exactly. And like that's what we're setting up for right now. So this is why, like, this is part 2 of topic models, right? Like, and this is why it takes forever to, and it's like this is really complicated. There's multiple steps to this. I haven't gotten to the stage where you should be understanding what's going on actually in the the engine of topic models, right? And it's like, and unfortunately, that's the part where there is not much intuition. I just have to work through the math, the intuition behind the math about why these things, like how you're able to sample from the posterior distribution. So hopefully, so what I'm hoping to do is, like, once we get through this second stage, right, then I'm going to actually recap, and actually in your mind, then you'll have both this first part and the second part, where then we can see as a whole how topic model works, right? You have this first step when you're figuring out a particular model you want to set up, and then you just solve the model, except it takes a long time to get these two pieces into play, unfortunately.
I see. Okay. And then I think maybe it's just been that, like, even doing the problems in the homework, the websites have not been actually as helpful as I'd imagine. So I'm trying to figure out where to get resources, and it's also like the class is a bit more abstract than the website. So that's probably why.
Yes. So actually, I think the online resources are really bad.
Okay.
So like, when I learned this, I basically had to learn this from first principles, and actually it helped a lot for me to read through the codes of some of the stuff. But obviously I don't expect people to do this. But so I think actually I do a good job of explaining. So I think, I unfortunately, I haven't, I've actually written some of the stuff down. So when we move to on Wednesday, when I actually go through the actual process, I'll send out some documents that I've written about sort of the nuances behind the actual sampling step. But I do think these topic models in particular, I think, is poorly explained. It's a little bit complicated. So unfortunately, I think you'll have to wait for me to tell you.
I think I guess that's this phase of the class. Okay. Well, thank you, Professor. Appreciate it.
Yeah, no worries. Yeah, okay, so intuition about question 1. Okay, so question 1. Where's question 1? I will be holding office hours, I guess, today. Is that what office hours are? But let me just, I haven't looked at question 1 in a long time. So yeah, so this is literally just calculating the posterior. Ultimately it's just sorry, it's not posterior. This is this is a conditional distribution over the words. basically what you want to do is you want to start with the joint distribution and then think about how to simplify it. I would start by looking at the single conditional distributions for one word, and then work through. So yeah, start with one word at a time. Like start with one word, just like calculate probability of WG1 equals C's given the rest, and that should be a nicer expression. And then you can think about what happens when you have 3 different ones. Hope that helps. Yeah. Maybe I'll talk a little bit more about this in the office hours.